Welcome back to Math for Technology. We are moving on in Chapter 12, and in the second section we're focusing on another type of exponential function. So if you look at the four that are written across the page underneath what do these have in common, they still look like exponential functions based on what we talked about in Section 1, but they should have one other thing in common that you notice. They all have what's called a base e. And on Blackboard there was a video talking about e and where it comes from, so if you're curious about why we even have e as a number, make sure you watch that video. So we want to make sure that you found the e button on your calculator, so whatever calculator you're using you need to make sure you can find. Now somewhere you should have maybe an ln button or just an e to the x button, depending on what your calculator looks like. So I have two different ones sitting in front of me. Both of them have what I can see as an ln button, and then if you hit the second ln it says e to the x. So make sure you can find that. I'm going to go ahead and give you the answers to these so you can practice. So e to the fourth is approximately 54.6. E to the negative 5 is approximately 0.01. That's definitely rounded. E to the 5.76 is approximately 317.3, and e to the negative 3.86 is approximately 0.02. So make sure you found that button and can do that. And do that before we move on into the graphing, because here we have to be able to plug in and find points. So similar to what we did when we graphed the exponentials in the last section, we're going to start by making a table. So I have my table with my x's and my y's. And so this time the difference, notice, is it says x is from negative 3 to 5. So instead of picking your own numbers, they want you to show on this graph all the numbers from negative 3 to 5. So our job is to plug all of these in and get the numbers and then put them onto a graph. I definitely suggest when you're doing these on your assignment, make sure you do all the plugging in first, get the table. That'll help you know what you need your scale to be. So when I'm plugging these into my calculator, I'm going to do 5e to the negative 3, 5e to the negative 2, 5e to the negative 1, 5e to the 0, 5e to the first, and so on. So let's take a second and make sure and plug all these in and get some answers. Okay, so I've taken the time to plug all of those into my calculators, and you can see them as they're running down the right hand side here. So I have to go all the way from, it looks like, approaching 0, and my highest number is 742. So I definitely don't want to do by ones, not even by tens, if I'm going to get all the way to 742. Maybe 50s. So go ahead and you would decide what scale you want to use to get there. So I'm going to do these by 50. But I'm going to go ahead and stay by 1 on the x. So my first one is negative 3 and almost 0, it's a quarter. Then I have negative 2 and just barely over 1/2. Oops, now don't forget we're going by 50, so it's going to be really hard because these are teeny tiny, and put that line back on there that just went away. Okay, so these, remember, are really small, and I'm just going to do my best. So it's almost 0 but not quite, almost 0 but not quite. Negative 1 is 1.8, but in the idea that these are 50, that really doesn't mean anything. Negative 1 is 1.84, it's still really small. 0 sorry, my graph is totally not cooperating with me here. Try this one more time. Okay, -3, -2, -1. Now I'm at 0. 0 is at 5, but these are 20s, so it's still really small. 1 is at 13, it's not even to 20 yet. 2 is at 36, so now we're starting to build. 20, not quite 40. 3 is at 100. 20, 40, 60, 80, just over 100. 4 is at 273, 20, 40, 60, 81. Oh, we're doing 50s. Man, my... Okay, so we're going to fix these. I'm sure you guys never do this when you're graphing. Everything's perfect. Okay, so 1 is at 13, and they're by 50s. So when it's at 13, it's still really small. 2 is at 36, it's still less than 1 box. 3 is at 100, so we're about 2 boxes. That's 100. 4 is at 273, 50, 100, 50, 200, 250, 273. And then 5 is about 700. So that's 1, 2, 3, 4, 5, 6, 7, 800, and I'm at 740 something. So it's definitely climbing very quickly, and sometimes it's really hard because we're really, really teeny tiny, and then we jump really up really fast. So we just do our best. Hope you do better than what I just did. Okay, let's try again. So I have my x and my y. Now this time they're asking us to go from -5 to 3. And this time it's 9.6 e to the -5 times x. So 9.6 times e to the -5 times -5. 9.6 e to the -5 times -4, -5 times -3, and so on. So I went ahead and filled out finishing the red part out, and then I went ahead and plugged it into the calculator, and let's look at these numbers. 6.9 times 10 to the 11th, that's in the billions. 4.7 times 10 to the 9th, now we're in the, actually this is in the billions, this is in the trillions. We're getting some huge numbers and then all the way down to 0. This graph actually would work best on what's called a semi-logarithmic graph, where they're not all the same apart, they change distance as you go along. So I'm actually not going to graph this one just because it doesn't fit very well on this graph. I'll double check the ones on your assignment and make sure none of them are huge like that, so it'll be a lot easier for you to do. But you have the concept. Okay, so let's go ahead and go down and see what else we've got going on besides graphing. So we have some formulas. We have the continuous compounding formula, which is S equals PERT. Of course, we need to define what those variables are. S, just like before, is our final amount or our maturity value. Our P is our principal or our beginning amount. E is remember, E is a number, it's not a variable. R is our rate, and it's our annual rate. And T is our time in years. Then we have one more formula that's given to us. This one is our exponential growth and decay formula. Depending on if it's growing or decaying on what your K looks like, it'll be either positive or negative. Your Y variable, the beginning one there, that actually is how much is left at the end. So this is our ending quantity. It's an E. Our C is our beginning quantity. K is our constant, that's the change. It can be either positive or negative. If K is greater than 0 or positive, then you are growing. If K is less than 0 or negative, then you are decaying. Then of course we have our T, which is time. Now in exponential growth and decay, time is not always in years. It could be in hours, it could be in minutes, it could be in years. It just depends on the problem. But it does change now. So we have two problems that we're going to work through. One of them is we're going to take radium and it's going to decay exponentially. It has a half-life of 1,600 years. How much of 100 milligrams will be left after 2,000 years? So let's just start with the first equation and plug it in. So since we're doing exponential decay, we know it's y equals ce to the kt. So let's plug in what I know. If it's half-life, so half-life, remember, means that, and maybe you don't know, but half-life means that half of what you have is gone. So if I start with 100 milligrams, like they're talking about, then when half of it's gone, I'm down to 50 milligrams. If I start with 50 milligrams, when half of it's gone, I'm down to 25, and so on. So I'm just going to start with 100, which means when I'm all said and done, I'll be down to 50. Starting at 100, E, I don't know what it's changing, how it's changing, but I do know that the half-life, the T, is 1,600. Now in order to use this K, I would need to be able to solve for it. So let's see what I can do. The 100 is multiplying with the E, so I could divide that. 50 divided by 100 is 0.5. Oops, that's gone now. I'm just left with the E to the K times 1,600. Now that's really all I know there. So let's go and let's mess with the next one. So I'm back to the y equals CEKT. So it says how much of the 100 milligrams is left. So I don't know what y is. I know I'm starting with 100. I still don't know what k is, but this time I know I'm going to 2,000 years. Well, if I could somehow get this EK 1600 to match up to the EK 2000, I could probably use this idea that it's equal to 0.5. So what is 2,000 divided by 1,600? 2,000 divided by 1,600 is 1.25. So what I do know is if I were to multiply this by 1.25, I would end up with EK to the 2,000. Well, the thing is though, if I do it to one side of an equation, in order to keep it equal, I would have to do it to the other side of the equation. So if my right-hand side is now equal to e to the EK 2000, I can replace this with the 0.5 to the 1.25 because they are actually equal according to this equation. So now I'm just going to plug that into the formula, into the calculator, 100 times 0.5 to the 1.25. So at the end of 2,000 years, there would be approximately 42 milligrams of radium left. Now that's one way to deal with it, and that's kind of thinking about how you would deal with it when you can't find out what K is, because our K is in the exponent. As we continue in this chapter, I'll show you another way to solve that one. Okay, let's look at the other example. $5,000 is invested. It pays 5% compounded continuously, so I have to use the continuously compounded formula. S equals PERT. How much can we expect to have after 10 years? So let's see what I know. S is what I'm looking for. P is what I started with. That's 5,000. E is, remember, a number, so I don't replace it. R is our rate, which would be 0.05. T is our time, and our time is in years. So we're going to do 5,000 times E to the 0.05 times 10. So at the end of those 10 years, I expect to have approximately $8,243.61. Okay, that's the end of section 2. Ask me any questions that you might have as you go along, and then I'll get back to you with 3. Have a good day.